Hey guys, welcome to Unit 13 Notes A. Today we're going to look at how to balance nuclear equations. First, we should probably talk about some different types of nuclear particles and who found them. So let's start off with a little historical perspective. The first person to actually discover radioactivity was Henry Becquerel, and I apologize for probably butchering that last name. But most people think of Marie Curie when you first start talking about nuclear energy. But this guy did find it first. Marie Curie provided a lot of our research and what we know about radiation, and eventually, because she didn't realize it was dangerous in the first place, it did eventually cause leukemia. But we appreciate all her hard work because now we know so much about nuclear particles. One other name to note is Ernest Rutherford. You may remember that he actually discovered the positively charged nucleus from his gold foil experiment. So of course, if he's studying the nucleus, he would probably be involved in nuclear chemistry. He actually helped determine the difference between alpha, beta, and gamma radiation, or three different types of radiation. So nuclear reactions, speaking of that nucleus, of course, involve a change in the nucleus. Usually when you change something in the nucleus, you produce not just a little bit of energy, but a lot of energy, which is why nuclear energy is so beneficial, because the amount of energy is exponentially greater than any other type of energy release involved in a chemical reaction. There are two main types of reactions. First, we're going to look at fission, and fission occurs where a heavy nucleus splits, and so the result would be two or more lighter nuclei. The opposite of that would be fusion. Fusion is where you have some smaller particles that combine together to form the heavier nuclei, fusing together. So fission versus fusion. Next, let's look at nuclides, which is actually just a fancy term for isotopes. The different nuclides of an element would be all of its different atomic forms, or isotopes, where you're looking at different mass numbers. Typically, if you have a small nuclide or isotope, the number of protons are equal to the number of neutrons, or at least pretty close, where some of the larger atoms will have many more neutrons compared to protons. There is one particular isotope considered to be the most stable. We kind of make fun of it, say that must be its magic number. It's just a certain preference for having this number of neutrons to this number of protons. And no, don't worry, you don't have to know every element's magic number. But you do need to know that every element has a preferred isotope, and the other isotopes, the bad isotopes, are typically radioactive. They would like to change their mass number in order to become the more stable or preferred isotope. So when you're looking at the low atomic numbers, typically the cutoff is around element 20, which if you notice on the periodic table is right where you start into your D block on the periodic table. So no surprise there. Our transition metals are going to start to behave a little bit differently. Once you introduce that D block, you do have a preference for more neutrons than protons. All right, so what are these three types of radiation? Well, let's take a particle that's unstable. By being unstable, I mean it has the wrong proton to neutron ratio. So if that happens, the unstable element will spontaneously or automatically decay. And these are the three different things we could get from that. First of all, we may get an alpha particle, which is composition-wise the exact same thing as a helium nucleus. An alpha particle contains 2 protons and 2 neutrons. Additionally, you may just produce a lot of energy, which is known as a gamma ray. Remember, gamma was part of our electromagnetic spectrum, way up high at the highest energy. The other type of radiation is known as beta decay, and the beta particle is specifically tied to the electron, although you may see protons and especially neutrons participating in some of these nuclear reactions. The beta particle is known as the electron. So we're going to use a table to kind of organize this. And yes, you do have to know everything that's on this table, but it does make a lot of sense. So let's look at the alpha particle. The symbol for alpha is the Greek letter alpha, and since it is a helium nucleus, we can use 4/2 to show that helium nucleus. That's literally what it is, where the top number is the mass of 4, and then the bottom number tells me the number of protons, so 2 protons would have a charge of 2. This is a pretty cumbersome molecule, and it's not going to penetrate or go through substances very easily. So it's going to say it has a low penetration. Now let's look at our beta particle. So the beta Greek symbol, or I can use my electron, which would not have a mass if we rounded to the highest or to the nearest whole number. And then it kind of is the opposite of a proton, right? So we can use a -1 to denote that in the atomic number spot. So this is our symbol for the electron. So we are going to be using these numbers, in case you couldn't tell, when we start balancing equations. So this is an important one to know because it's a little bit weird. 0 over the -1 for the electron, representing that negligible mass because it's so small and the charge of -1, excuse me. So it's a much smaller particle, so it's going to be able to penetrate a little bit further, the low to medium penetration. Now let's look at our gamma ray. So not having any mass or any effect on the proton, and using the symbol for the gamma Greek symbol, this little Y-shaped guy. Gamma is not a particle, it is just energy. Whereas these two types of radiation are mass, or matter I should say, this is energy, completely different. So the mass is actually 0. Instead of just being negligible, it literally doesn't have a mass because it's energy. And there is no charge associated with energy, of course. So this being a pretty free-flowing thing with a lot of energy is going to go the furthest. So we're going to say it has a high penetration. Now we mentioned that protons and neutrons may also play a role, so we need to determine their numbers as well. So a proton would have 1 as its mass, and would be like, how many protons are in a proton? Like the atomic numbers count of protons, so the number 1 is also used at the bottom. Remember, proton is the same thing as hydrogen, back to acids and bases, so we could call it hydrogen or proton either way. That's what it is. It is literally 1 proton. So the mass of 1 proton is 1, and the charge would be +1. So the proton is going to behave kind of similar to the electron in terms of penetration, so going about a low to medium. It's a pretty small particle, not super heavily charged, so it's going to go through a little bit further, but still not go as far as just pure energy, right? Now let's look at the neutron. So a neutron will contribute 1 to the mass number, and it's not affected or doesn't affect the proton count, so we would use a 1, 0 for the neutron. And it literally is a neutron. There's no other way to look at it. So the mass was 1, and the charge of a neutron is nothing, so 0. Surprisingly, the penetration of a neutron is very high, even higher than the gamma ray, which is kind of the problem when we start looking at what carries on these chemical reactions for nuclear equations. The neutron's kind of the bad guy. Remember, stability was all about the proton-neutron balance. So if you take a stable atom and you start messing with its neutron count, you're going to then make it unstable. And so this can create what we call chain reactions, where things are continuing to become radioactive because neutron's the bad guy. So let's look at a kind of picture example of what I mean by penetration. Alpha having the lowest penetration would be blocked by a piece of paper, blocked by your skin, fairly innocent type of radiation. Whereas beta, and remember the proton would be about the same thing, could be blocked by wood. So sheltering in your house as opposed to being outside would be sufficient protection. Then you have gamma radiation, and even worse yet, the neutrons themselves, which can create radiation where there wasn't any before. So these need special barriers. They're going to make it through the walls of your house. They need reinforced concrete in order to contain your gamma radiation or your neutron. If you remember, gamma radiation was way down on the electromagnetic spectrum, kind of close to X-rays. Think about the big metal, or not metal, big lead, well, I guess it's metal, big lead like aprons that you have to wear when you go in to get X-rays or for your dental X-rays, stuff like that. It's all trying to block the X-rays, and the gamma rays are even more energetic than that. So this takes a lot because the penetration is very, very high. So by penetration, we're talking about how much stuff it can go through. Now let's get into actually balancing the reactions. In order to write a balanced nuclear reaction, we're going to need the top mass numbers to be equal on the reactant side versus the product side. And we need the bottom atomic numbers, let's just say, on the bottom part. I know we have that -1 for the electron, but whatever the bottom number is, we also need those to balance reactant versus product. So we're trying to make sure we're balancing not only the atoms, but the protons, neutrons, electrons instead, since we're changing the nucleus. So this is a little bit different. So here's our first example. Radium-226 transmutates. Now they use all kinds of crazy words in these word problems that basically mean change. So transmutate, transforms, changes by alpha decay. So the first thing I want to do is figure out what radium-226 would look like with that mass number, atomic number setup. So the chemical symbol for radium is Ra, and this isotope format, you may remember, gives you the atomic number of 226. So now I need to determine the atomic number from periodic table. So we've got our radon down in the corner has an atomic number of 88. So remember, with this format, you had to look up your own atomic number. So now it's going to change or transmutate by alpha decay. Decay is another indicator that that alpha particle is on the product side. So an alpha particle was He with a 4 on top and a 2 on the bottom. That's what an alpha particle is in the equation. So this is why we had to go over that table so well. Now to solve this, I need to figure out what the top and bottom numbers are for my product. So I have 226, a 4, and I need to figure out the number of my next product. So what I know is 226 should equal 4 plus something. The top numbers combined should be equal on either side. So I'm going to set 226 equal to the 4 and the other thing. So what other thing, what other number, basically what is x? We would have 222. Now let's look at the bottom numbers, where I have 88 and 2, and now I need to figure out what the bottom number is. So I'm going to set 88, the only number on the left, equal to 2 plus the number I'm trying to find on the right. So what plus 2 is going to balance with my 88? Well, that would be 86. So now I need to figure out, okay, what is the chemical then? What is the element that I've changed into? It produced this helium particle, and I lost 2 protons along the way. So instead of being element 88, now it's element 86, which is radon, abbreviated Rn. So you balance your numbers on the top, you balance your numbers on the bottom, then you use the bottom number to predict what the element is. So this one, we have 22688 radon producing the alpha particle, and 22286 radon for alpha decay. So you could write your alpha particle if you want to, but you know how much we need these numbers. I've also seen this blended together using the 4 and 2 on the alpha particle. Either way is fine, but you have to be able to use those numbers to determine what your product is, which in this case was the radon. All right, let's look at, let me scoot this over a little bit. Let's look at beta decay. So now I have boron 12 going through beta decay. So I'm going to start by turning the boron 12 into that chemical symbol. So the 12 would be my mass number on top, and I have boron, chemical symbol B. So that's towards the top of the periodic table with an atomic number of 5. It's beta decay, meaning the beta particle will be on the product side. By the way, the word bombardment would mean that that particle is on the reactant side. So if I said I had beta bombardment of boron, then I would have the beta particle on the reactant side. But because it's decay, it's on the product side. All right, so what is this beta particle anyway? So the symbol for that was the 0 minus 1 for the electron, showing a mass of about 0 and kind of an antiproton, so a -1 over here. Now I need to do my math very carefully because of that negative sign. So on top, it's not too bad. I've got 12 on the left, 0 and something on the right. So what's my something? Of course, 12. On the bottom, you got to be really careful. I've got 5 on the left and a -1 on the right. So what would I add to -1 to get 5? So that's actually going to be 6. 6 minus 1 is 5. So that means 6 would be element carbon. And so we would write our C here. So be really careful whenever you have that -1. Because that actually is going to mean you're increasing your atomic number. All right. So there we go, showing the carbon as a result of the beta bombardment. No, beta decay, sorry. Okie dokie. Last type of radiation is our gamma particle, or not particle, gamma energy, so gamma radiation. It doesn't really look like a whole lot is changing here. I have my cobalt that I start with, and in the end, the cobalt still has the same mass number and the same atomic number. But you can see here that we've released a lot of energy. Gamma particles are pure energy. So my first question is, which one would have more energy? My cobalt reactant or my cobalt product? My cobalt reactant would have to have more energy because it then turned into something with less energy since I was able to release energy. So think conservation of energy. I had to have all of this energy in the cobalt to start with in order for it to break down out of the cobalt. So what would be different about these two atoms actually? Well, this ties all the way back to Unit 2 when we talked about ground state and excited state. So remember we had the nucleus, we had a low energy state, and then we had a high energy state. And the electrons liked to be in the ground state. According to Aufbau's principle, they hang out in the lower energies, but then we could excite it. It's not going to stay there, again, because of Aufbau's principle. And so it's going to then return back to the ground state. In order to go from excited state to ground state, there has to be a loss of energy. And that energy is released in the form of a photon. Notice a connection here? The symbol for the photon is the same as the symbol for the gamma radiation. All that would have to happen is this would have to produce a lot of energy in order for it to be considered gamma radiation. If it produced less energy, we could say possibly it produces one of the colors of visible light, or even all the way down to the AM radio waves. But if we have a large quantum of energy being produced, then that energy being produced would be our gamma radiation. So kind of a cool connection there. So we have basically the electrons in the excited state when we start gamma radiation, and the electrons have returned to the ground state, releasing large amounts of energy. And that's our gamma radiation for you. So now we've tried one of each. We're done with balancing nuclear equations. The next part of the nuclear notes will be all about fission and fusion. We'll see you there.